I'm not used to mic. It's a great pleasure to have Professor Xuguang Wang. Today she's going to talk about state of art. Also, one of the things she does so well is to R2O, research to operational, which is very difficult to do, but she does so well. So she's going to talk about the state of art of data assimilation today.
So thanks, Kyle, for such a generous introduction. And so, let me see, okay, working. So I'm currently working with a group of students and early career scientists on data assimilation and predictability problems ranging for a variety of scales. So, so I'm going to actually talk about our progress over the last 2 years with the emphasis on a method called Ensemble Variational hybrid data assimilation. And I will talk about a variety of scales applications from global prediction and convection-allowing hurricane prediction and also convective severe weather prediction over the continental US. Can you hear me? Is the mic on or not? Okay, good. All right, just make sure. It's not on. It's on. Okay. Okay, thank you. All right. So before I really start to share our work, I really want to acknowledge all the students and postdocs that I have been working with so far. So I feel very lucky to work with them. And so I will highlight their names with a star while I advance the slides, so you will see their contribution. But unfortunately, I'm not able to talk everybody's work due to the time constraint. So actually, because of our interest on data assimilation for a variety of scales and our strong interest on transitioning our research to operations, as Kyle mentioned, over the last 10 years, we have actually established very extensive collaborations with many NOAA labs centers all over the country, from here like EMC, from Boulder, Israel, and also Miami, AOML, and also Norman from NSL and also SPC. So we really, really value the collaboration. Okay, just in case you're not working in the area of data assimilation, I prepared just 2 slides to give you an idea what data assimilation is trying to do and the significance of data assimilation. So conceptually, data assimilation is pretty easy, and it is actually a statistical approach, and it's also an objective analysis approach. The goal here is to optimally combine 2 sources of information. One is coming from observation, the other is coming from model forecast. You can also call it as a background. And the goal here is to actually produce this end product analysis as accurate as possible to estimate the true state. Okay. So data assimilation actually already become, in my opinion, a sub-discipline in geoscience. So over the last several decades, it actually drastically advanced numerical predictions for weather, for climate, for hydrology, etc. Okay. And we also can create a long record reanalysis through data assimilation for climate study and for model evaluation. Data assimilation can also help us to optimally design observation network. And will help us to understand the model errors, improve the numerical models, for example, the model physics parameterization. It will also help us to understand predictability and dynamics of the system we're interested in doing. It will also help us to advance data science. You know, we're in a big data era, so data assimilation is a natural bridge, between data and the model. And also going to help us advance estimation and the information theory. So that actually draws my attention for data assimilation because it's really important. This area is really, really important. Okay, so what are current challenges for data assimilation? I just used 1 slide to briefly summarize several bullets here. First of all, how to do data assimilation in a system that houses many scales, including a couple system assimilation, is still not clear. So we still need to do a lot of research on that. And current use method normally assume a Gaussian or linear assumption. So, however, a lot of problems, they are violating the assumptions. We have methods that can treat nonlinearity and non-Gaussianity, but normally they're suitable for small systems. But for geoscience or meteorology, we're dealing with a high-dimensional system. How do we treat that in a high-dimensional system? And also, as I mentioned earlier, you're trying to combine two source information from short-term forecast or background and observations. One of the important quantities for this combination is to know or estimate the errors in your observations and also the model forecast. How do you do it well? I mean, you have to know how to, sample the model errors. You also have to deal with sampling errors if you're using ensemble approach. The last one is, as many of you are aware of, we're actually going to have a lot of observations from new remote sensing in situ platforms. And with increased computational powers, we're going to increase model resolution and the number of ensemble members. How are we going to use data simulation to harness this big data coming from both observations and models? So that's also a big challenge. Okay. So what are we interested in? What are we mostly excited about for data simulation? We actually have a broad interest for our lab for data simulation. So we're interested in developing new techniques and novel methodologies. We're not just applying existing methods. We're trying to advance the theory and advance the new algorithm. We're also interested in applying these new techniques for global to convective-scale prediction and assimilating a variety of observations from radar, satellites, ground-based remote sensing, aircraft, etc., to improve NWP, basically, improve numerical variable prediction. We are also interested in using data simulation as tools to understand predictability and dynamics, and also for a variety of scales. And one thing that Kyle mentioned is that we are also excited to transition our research to operations. So we'd like to see, the impact from our group and from transitioning the research to operations to improve the operational forecast. Okay, so I'm going to just show some examples about our ongoing work. I'm not going to talk about all this during today's seminar, just give a couple samples, but I thought I would go through this, so if you want to talk more with me on these topics, I'd like to do that while I'm here. So actually, back in 2009, our research lab participated in this multi-institutional collaboration on the development of the EnVar hybrid system for the GSI. GSI stands for the Operational DA System in the US. And that collab effort led to the operational implementation of the 3D and 4D VAR back in 2012, 2016, and NOAA, Maryland, and NASA, they're all partners of this. And so after that, we developed other methods to improve the EnVar system for global prediction, including, for example, the cost-effective method increased the background ensemble size for the EnVar, which I will talk about today. And we also developed the multi-resolution ensemble EnVar method. And other than that, we're also using simple model as a tool to advance like the data summation method or theory. For example, the recent work includes the high-rank ensemble transformer common filter. We're also currently working on scale-dependent localization. That's part of the challenge under multi-scale data simulation. And for hurricane data simulation, so our lab in collaboration with NOAA has developed this fully cycled EnVar system for HWRF. HWRF is the US Operational Convection-allowing hurricane prediction system. And we try to review, okay, whether the new approach is able to improve, for example, intensive forecasts. And that system became operational. I mean, the system, based on what we built, became operational last year. And we then used the system to study the impact from a lot of observations, including situ remote sensing in the core observation, which I will show briefly today. And one significance of data simulation, as I mentioned earlier, is you can use that to improve models. In this case, we use this new DA system to review the physics problem in the HWRF model. And we also trying to use data simulation to understand the process, okay, fundamental process for tropical cyclone rapid intensification. For convective scales, since I'm in Norman, naturally I became interested in convective scale data simulation. So we recently developed an algorithm to assimilate radar reflectivity directly using the EnVar. And we implement the method for the 3 US operational convection-allowing prediction system, HER, then CONUS, and Wang forecast system. And we're also very interested in, towards DA research under close to LES resolution. So we start with some research with sub-kilometer analysis and to see the impact of that on tornadic superstar prediction. And we use DA to understand, for example, nocturnal correction process and understand how the nocturnal convection system is maintained or initiated. And a lot of observation platform for radar is also adaptive, so we're trying to study the target observation method for convective scales. So I'm not going to talk all of them. I'm going to just show several samples, but what I'm going to talk today will be based on the EnVar data simulation method. So it's a hybrid between ensemble variational approach. So briefly speaking, the idea here is you're trying to incorporate ensemble covariance in a variational system using the extended control variable method. And so the idea here, we are trying to actually combine the best aspects from a pure ensemble common filter and a pure variational system. That's why we call it a hybrid. We're trying to bring the best out of both. And we have done some work to show this solution is equivalent to a solution where you just directly combine static covariance and ensemble covariance. So you might have heard about the 3D and 4D EnVar. So those are the two flavors under the EnVar. So I have three parts. So part one will be more on global. I just show one example. Part two more on convective-scale radar, and part three more on hurricanes. So just to give you an idea what we are excited about for each area. So for global, brief background, as I mentioned earlier, back in 2012, 2016, National Weather Service NCEP actually operationally implemented 4D EnVar in place of the 3D EnVar at that time. And studies have found significant improvement of the forecast analysis because of implementation of the new DA system. So since then, we have worked on further improve the systems. I'm going to just share one method we tried. This is called the valley time shifting method. The idea is to increase the size of the background ensembles. Okay. So how does it work? So like all the ensemble-based assimilation, like you may have heard about ensemble common filter, 4D EnVar, or whatever. So all these methods struggled with the sampling error when they estimate the background error covariance due to the use of limited ensemble members. For example, we are using 80 in operations. That's still very limited. You're going to struggle with the sampling error. So you could actually increase the size by directly running more ensemble forecasts, but that's very costly, okay? So the valley time shifting idea is, okay, at 60, we're creating analysis. Right now, we have 80 members. So instead of running directly 240 members, for example, for the background, we're trying to increase ensemble size by shifting the 3-hour forecast to 6-hour and 9-hour forecast to 6 hours. So automatically, we are tripling the ensemble size from 80 to 240. So depending on what you're doing, you're shifting the entire member or shifting the perturbations. We have two names here. VTSM M means I'm shifting the member. P means I'm only shifting the perturbation. The mean is still the same as before. So one of the challenges for global prediction is there are so many different phenomena with different predictability, different scales. How do we, it's very likely, okay, one method is not working for all. So the idea here is to see whether the VTSM and VTSP, how they work for different scales, for example, tropical cyclone forecast and global forecast. For example, I have a tropical cyclone case here. Using the VTSM method, you can see it's sampling the background error better. However, if you apply the same method for like a mid-latitude trough, for example, it's actually doing something harmful. It's actually making the background sampling become more non-Gaussian, which is it's going to degrade the analysis. So we're also trying to understand, okay, why the VTSM, VTSP going to have positive and negative impacts for the global and hurricane track forecast through this study. So this is our experiment. Basically, this is our baseline running 80 members. So we're trying to mimic the operational system as close as possible, but we're running at a relatively reduced resolution, and we're using operational data from in situ satellite. And ensemble 240 is, okay, I'm just going to increase the ensemble size from 80 to 240 directly by running more members. That's more costly. And these two set experiments, I'm increasing the size from 80 to 240 by using a cheaper shifting method. Okay, all right. So this is the cost. Okay, you cannot get around the problem if you're a computational cost issue when you're dealing with NWP. So this method is almost 3 times compared to the reference. And this shifting method, depending on how much you want to shift, 1 hour, 2 hours, 3 hours, and the cost is somewhere between 23% and 27% increase compared to the reference. Okay. So then let's look at the performance. And this is the 6-hour forecast verification. Okay, and this is for temperature, wind, and this is for the perturbation shifting method. This is for me, and it's a full member shifting. And what's shown here is actually the relative improvement relative to the Ensemble 240. Okay, basically I want to see the how much the the cheaper shifting method is going to recover the improvement relative to Ensemble 240. So if you look at closely, you will found the dash blue line. Actually, this is the VTSP method. Okay, perturbation shifting only with 3 hours. That one shows the most consistent positive improvement. Okay. Now let's look at the longer forecast. So from day 1 to day 5, verified against the European Center analysis. So, okay, this is for temperature and for wind. And this is using the baseline as a reference. Basically, whenever you're seeing blue color, that means you're making improvement. Whenever you see red color, that means you're degrading. So this first column is, we directly increase ensemble size from 80 to 240 by running more members. It's costly, but as expected, it's better. Okay, it's improving compared to the baseline. So these 3 columns are the shifting method, shifting the members, the VTSM method. So you found majority improvement is about 100 millibar, and below that you start to see degradation, especially when you start to use 3-hour longer shifting window. Okay, so that's for the VTSM. What about the VTSP? Only shifting perturbation, but you're caving the background mean at 6-hour window. Okay, so interestingly, it's different compared to using VTSM. Here you are seeing more consistent improvement using the perturbation shifting, especially when you're dealing with like 2-hour shifting. Okay. So then the question is why they're behaving so differently. Okay. So we're trying to do a lot of diagnostics to understand that. So as I mentioned earlier, for data simulation, one of the important quantities to estimate, for example, the error from the model, short-term forecast of background. So in particular, for the current EnVar method, this is one of the key quantities, which is background ensemble correlation. Okay, so using shifting method can improve this accuracy of the ensemble correlation. So we want to see to what extent VTSP is improving that or VTSM is degrading that. So we first need to define a metric which is called ARC. Basically, we are using Ensemble 240 as a referencing truth. Okay, and we see how the ensemble, the 80, the baseline experiment is performing, to see whether this metric is making any sense. So x-axis going from left to right means your correlation is increasing, and ARC, the higher the worse. Higher means you have a poor estimation of the correlation. So what we're seeing here is basically the ensemble approach has a tougher time to estimate small errors, small correlation. Okay, when you have less signal to noise ratio, you tend to struggle more. And also has a tougher time to estimate cross-variable correlation. Okay, that's what we found from this figure. And then we apply this metric to evaluate VTSM, VTSP. Negative means it's degrading, and positive means it's improving. So basically what we observed is, VTSM indeed is showing degradation on the correlation estimation, especially for small value of correlation. VTSP, on the other hand, is improving the correlation estimation. So that's consistent with what we found earlier, right? The forecast is improved with using the perturbation shifting only. So this is just an example to show why. So this, for instance, VTSP is improving the correlation while this guy is actually degrading. So this is the referencing truth using 240 members, and this is TT correlation, okay? And on Ensemble 80, you can see due to sampling error, you have some negative correlation here, okay? And if I use the shifting perturbation approach, it becomes more like Ensemble 240. Okay, so some of the noise is reduced. And if I use the member shifting, okay, which was degrading my forecast, I found this correlation structure is so different compared to Ensemble 240. Very likely because you're shifting the mean as well, so the correlation is not actually representing the background error correlation properly. Okay. So then we also look at the other verification or diagnostic. Look at, for example, the effective rank in the ensemble covariance. So we use the E-dimension metric to estimate the effective rank in the ensemble covariance. This is from 80, so the higher the better. So 80, okay, that's ensemble 80. Ensemble 240 has a lot more, okay, compared to ensemble 80 as expected. And these two groups are from member shifting and perturbation shifting. So for each, given interval, time shifting interval, the VTSP seems to be having more rank, or it's compared to VTSM, especially with a longer shifting interval. That also seems to be consistent with the forecast improvement by the VTSP. Now we have hurricane forecast over the 10-week period. We actually had 22 tropical cyclones. And so we start to look at the tropical cyclone track forecast. So we found something very interesting here. So the black line is the reference, or baseline Ensemble 80, okay? And the orange line here, okay, is directly increasing from 80 to 140. So it's costly, but it does improve the track forecast. So these dashed lines are the VTSP. So remember, it's cheaper compared to Ensemble 240. However, if you look at it, you found it's actually, the scale is actually comparable to the more costly Ensemble 240 method. And if you look at the solid lines, if you look at this one, which is shifting by 3 hours, the VTSM, okay, is even better than the Ensemble 240. And remember, both VTSP and VTSM are cheaper compared to Ensemble 240. So this result is very interesting. Yes?
Why the VTSM for the HA83 difference is the best?
Yes, so this is 1 hour shifting. This is 2 hour, this is 3 hour. You can see quite a bit of diverse sensitivity there. So the reason is shown, yeah, you can imply here. So this basically means, the reason is better because it was able to better sample, for example, the shifting, the timing and phase error of hurricanes. Yes, yeah, exactly. So it's indicating 1 hour is not enough for sampling that. Yeah. So it's actually demonstrated in this figure. This is showing the ensemble spread versus the location error for 6 hours. So we also plot it as a rank histogram just in case you want to know what rank histogram does. If it's flatter, that means your ensemble is doing a good job to reliably sample the error. And for both the Ensemble 240, Ensemble 80, Ensemble 240, you see an interdispersity. Basically, your ensemble is too narrow, so it's not able to sample the possible error in your background forecast. By doing the shifting, you're capturing, for example, the timing and phase error better. So that's why your histogram becomes flatter. So that's hopefully answering your question. Yeah. Okay. So we're trying to, once you're trying to implement it through operations. So that's one of my goals here. Yeah, because it's cheaper and need very small multiplication for the system. Yeah. Go ahead.
So earlier you showed that VTSP is better than VTSM.
Yes. Yeah. Exactly. Yes. Yeah. So this is a good illustration. We're dealing with a multi-scale problem. So it's better for hurricanes, may not be better for global scales, for example. So I think it's illustrating the challenge here. But if I want to make a recommendation overall for the operations, I would recommend VTSP with 2 hour shifting. So it's still showing, for example, improvement of track error, even comparable with Ensemble 240. It's still also improving the global forecast. Yeah. So okay. Next, okay, I'm going to switch to another topic. Basically, I'm going to zoom in, okay, from global to storm scales. And so basically, so when I moved to Oklahoma, I became very interested in convex field data assimilation. Not only because I live here, Tornado Alley, but also because I'm really, really intrigued by the challenging problems doing data simulation for convective scales. So, and for convective scales, one of the important observation platform is radar. So over the CONUS, we have 330 million radar observations every 5 minutes. And with the dual pole upgrade, the number of observations is at least doubled. So we have a lot of data, okay? And so let's see whether I can do this. I'm also showing an example. This is our OU's Advanced Radar Center's research radar, okay? So this is observing a tornado 2013, May 20th. And so basically, you're seeing very, very fine resolution observations with spatial resolution around like 30 meters and temporal resolution like 10 or 20 seconds. So we're basically dealing with assimilating movies if we are trying to ingest this observation into the model. So this actually really, really pushed the limit for data simulation. And we all know the goals are, and it's also providing very, very high resolution data in both space and time. For example, if you're on the CONUS mode and it's 5 minutes and you have spatial resolution 500 meters, 2 kilometers. So we have a lot of data that can sample convective scales. Okay. So what are the challenges for convective scale data simulation? So first of all, your observation operators are complex, okay, and often nonlinear, especially when you're dealing with radar observation and cloudy radiances. And in this regime, the prior and observation are becoming more non-Gaussian, okay? And we also need to rely on the cross-variable relationship in the update because our remote sensing observation is not directly observing model variable. And the performance will heavily depend on the performance model, for example, microphysics scheme. And these two are associated with the advancement of observation platform. For example, we're dealing with very high resolution observations, okay? And this is really pushing the limit for data simulation. And the system we're looking at is also very short-lived and, no more than 1 hour, for example, with very short predictability. And also, convective scale prediction itself is a multi-scale problem. You have to estimate storm properly. You also have to estimate supporting environment properly. Otherwise, even you put storm right, and the environment is not supporting that, and then the storm will quickly collapse, okay? So in the past couple of years, our lab in collaboration with NOAA has developed this direct radar data simulation capability for all the solvers in GSI, and we tested within US 3 convection-allowing prediction system, for example, HER, and then CONUS and Wang forecast. This is more like supercell type of forecast. Okay, this is 18-hour, this is targeted for 60-hour. So what we did is to basically extend both ENCAP and EnVar to the convection-allowing model, for example, WRF. And this is going to enable the, for example, HER system to ingest convection-allowing model's own ensemble. Right now, they are using coarse resolution GFS ensemble. Okay. And we also developed capability to assimilate radar directly. For example, we add hydromedia and vertical velocity as data variable. We actually developed the reflectivity and velocity observation operators. And another thing I want to talk more later is we developed this direct reflectivity simulation in the EnVar. The current operation system is using cloud analysis, so we're trying to see, okay, whether this more costly approach is going to be, how much is this going to improving compared to the cloud analysis. So we have shared this with a variety of NOAA collaborators for them to test on their system. So I'm going to, earlier I talked about the challenge associated with nonlinearity and Gaussianity. So I'm going to show you one example. This is specific for radar reflectivity simulation under the EnVar. I'll show you the method we propose to alleviate the issue, and also show an example with the tornadic supercell. And then I'll show some comparison between this new approach compared to the operational cloud analysis. And then I'll show this interesting work, and basically we're trying to do 500-meter grid spacing data. We want to see to what extent it's helpful with such a high resolution simulation. So for EnVar, this is the typical cost function. You see people actually linearize observation operator. Okay, the H is linearized observation operator. But if you look at a radar reflectivity operator, it's a highly nonlinear function of the hydromedia mixing ratios. Okay, so this could incur problems during the variational minimization because the cost function contributed by reflectivity and radial velocity, they can be very different. So this will produce very inefficient minimization, which will lead to underestimate of hydromedia increments. This is especially true when you're using a very small number of hydromedia mixing ratio. We try to alleviate the problem by taking a log. It's improving the minimization. However, it's introducing another bigger problem. Basically, you're producing anomalous large hydromedia increments. This is because, you know, if you do transformation in log space, doing the DA there and then transform back, it simply is not a reversible process. Okay, and so it's not working by just doing the log. And another problem is coming from just linearization of the nonlinear operator itself. It makes this underestimation, overestimation problem even worse. Okay, so how can we do something to alleviate this problem? So what we did is we simply augment the state variables by directly including reflectivity as a state variable during data simulation. And this way, our operator is identity matrix, and the gradient issue is not there anymore. And you're also following the nonlinear relationship between hydromedia and DBZ, the reflectivity. Okay. So we are trying to test this with the 2003 May 8th Oklahoma tornadic supercell. And this is a F4 intensity tornado, and it's lasting for like 30 minutes. The supercell itself maintained pretty well beyond 20Z until like 0Z. Okay, all right. So let's see what's going on here. So we're running ARW at 2 kilometer grid spacing and simulating radar observations. This is our experiment domain. So we're really zooming in. Okay, this is Norman, Oklahoma over here, by the way. And so what's showing here is the 1 hour forecast of the vertical velocity and vorticity at 4 kilometers. Okay, for 3 assimilation methods. This is newly proposed method. And basically for storm scale community, one thing they look at for the forecast is whether the tornado producing supercell was maintained properly or not during the forecast period. Oftentimes we observe storm here, but the storm quickly collapsed. Okay, it was not able to maintain. So that's one thing we're looking at here. So if you look at this animation one more time, okay, and then you look at this guy using log transform, it quickly dissipated and replaced by a spurious storm from behind. Okay, and here this one is just use original hydromedia as the state variable. It's much better compared to the log transform, but compare this with the new approach, we're still not able to maintain the storm as long and strong compared to this new approach. So I always encourage students to interpret their results, okay, to level they feel comfortable, not only from data simulation theory, but also from dynamics, for example. So why would this method was able to maintain storm better? So if you look at the analyzed grapples, okay, you see this guy has more extensive coverage of the grapple. This has much less compared to this one. And correspondingly, you have a too strong a cold pool here and too weak a cold pool. So these two methods was not able to maintain the constructive interaction between the surface circulation and the mid-level mesocyclone compared to this one. That explains why these two were not able to maintain a storm as good as this guy. Okay? So everything comes together, DA, data simulation, and storm dynamics. Okay, so with that, encouraging results, we try to implement the method into operational convection-allowing system, for example, HER and also NAM. Okay, those are the two leading convection-allowing prediction systems in operation in the US. So yeah, this is like we applied over the full CONUS domain with 3 kilometer grid spacing, so a lot of computing here. Okay, so this is what we found. This is only with retrospective cases, and basically the blue line is using the EnVar to assimilate reflectivity, and this blue line is cloud analysis, the current operational method. And green line is I'm not simulating any reflectivity in any fashion. So one thing we noticed that EnVar tends to overall verify better than cloud analysis. Okay, this is basically strength score, the higher the better. This is for reflectivity forecast verification. This is for precipitation verifications for 3 different thresholds. And still, cloud analysis is improving upon not doing any assimilation of reflectivity, although the improvement is limited for the first few hours. Okay, so that's pretty encouraging. But still, why would that happen? Why would EnVar reflectivity simulation we propose is working better? So we found 2 reasons based on our diagnostics. The first one is the EnVar approach is able to suppress spurious convection by assimilating radar reflectivity. The current cloud analysis, okay, is not able to do that. Okay, so this spurious convection will, of course, degrade your skill for forecast later on. And another reason is the EnVar method. Okay, because it's using the covariance between different variables derived from the ensemble. When it's simulating reflectivity, it's also correspondingly able to update the dynamic field like updraft. Okay, but for cloud analysis, it can insert, for example, hydromedia TNet, but it's not able to update the dynamic field like updraft probably. So you put hydromedias here, you're not putting a supporting updraft, your storm is going to be quickly collapsed because of that, so during the subsequent forecast. So that's very encouraging. Actually, we at Anomaly, we have this known as Hazardous weather test bed. We take advantage of that and test the system, a new method, in, like semi-real-time session. Okay, this is this spring actually we ran our system. We call it OU map ensemble for the entire 5-week period, and so far the subjective evaluations by the forecasters and participants actually evaluate the system pretty well. So this actually laid the foundation for us to operational transition system to operations. We have a plan to do it in 2020 in collaboration with NOAA GSD and EMC for that. Okay. So one thing we are quite excited about, okay, we have such fine resolution observations that are shown earlier. And early studies have also shown to really resolve convection motion, we really need something with grid spacing like from 10 meter to 100 meter, very, very fine resolution, okay? So one thing we want to see is there really a need to do data simulation at such a fine resolution? People have done fine resolution simulation or prediction, but they normally just downscale from a cost resolution analysis. So we're interested in finding, okay, to what extent using finer resolution analysis is going to improve the subsequent forecast. So, but it's of course expensive. You cannot run all members with 500 meter resolution, right? It's too expensive. So we extend the GSI EnVar dual resolution capability. So our analysis produced at 500 meter grid spacing, so tiny, okay? And ensemble is still at 2 kilometer resolution, okay? All right, let's see what's going on here. And this is our experiment design. Basically, this is the flow chart for the EnVar assimilation. You're doing this every 5 minutes, assimilation, and you're creating your analysis at 2 kilometer resolution by ingesting ensemble at 2 kilometer. So at the end of simulation, you're creating like 2 kilometer resolution analysis. And then you downscale that and you create a 500 meter resolution free forecast, okay? And this experiment is called dual resolution. Basically, during this decycling process, your control analysis forecast is actually at 500 meter resolution. Although you're ingesting 2 kilometer ensemble, at the end, you're creating analysis of 500 meter resolution, and you just directly launch a 500 meter free forecast. So we're trying to see whether this high resolution analysis can actually improve the subsequent forecast or not. Okay, so this is the same case, okay, May 8th, 2003, Oklahoma, OKC connect supercell. And this is what's happening in reality. It started with F0, F4, F1 intensity. It briefly decayed and then intensified quickly to F4. Okay, so we're trying to see whether this, trend for intensity change is captured well for the forecast or not. This is using the cost resolution 2 kilometer experiment. So you can see the dual resolution experiment indeed was able to capture this re-intensification compared to the 2 kilometer. So this showing, at least for this particular case, there's a need for certain prediction to use 500 meter, fine resolution analysis. Okay. And then again, we're trying to understand why the forecast is improved I'm not able to show the step-by-step diagnostic, but you do see a difference, a significant difference between the two analyses using dual resolution and the 500 dual resolution approach and also 2 kilometer. So, and this one is not too much expensive compared to that because this is only having one member run 500 meter. So you see, for example, a stronger and broader mid-level downdraft and in dual resolution and over the rear flank region. And you also see a stronger outflow surge trading the rear flank gust front in dual resolution compared to a single resolution. So when we did diagnostic from here, we found, okay, indeed, this were able to translate into subsequent forecast differences. Okay, so that's, okay, interesting. And the next part is the hurricanes, so convection-allowing hurricane predictions. So I'm going to only briefly show 2 topics. The first one is we developed this cycled EnVar thesis for HWRF, and this became operational. So we work with Anomaly, we have this hybrid system based on this operation last year, and we're trying to understand, is intense forecast improved using this new DA system, or if that's the case, why? And I also want to give you another example of the power of using data simulation to review model physics error, especially associated with the rapid intensification of hurricanes. So yeah, I'm not going to go to the details here. Basically, this is what the cycled EnVar hybrid system looks like with HWRF, and it can do continuous cycling following a storm. It's dual resolution. You have EnVar flavors, 3D and 4D, assimilating all the operational observation, including tail Doppler, job sounds, flight level observation, satellite radiance. So far, just clear air. We also integrate that with the current vortex modification relocation package. So one thing we want to see is really, is this having any potential to improve hurricane intensity forecast? Because that's one of the leading challenges in hurricane prediction community. So this is Edwards 2014. This is the black line is the reality from best track data. And so the operational HWRF is in red. You're not seeing, basically, it's instead of intensifying right before, after initialization, it actually spin down and then go up. So this basically will degrade the intensity forecast. And the hybrid approach was able to alleviate that. It's not completely solve that, but it's able to alleviate that problem. So then we are trying to see why it's improving the spin down issue. So basically, what's shown here is the average azimuthal inertial stability and radial wind, and also tangential wind during the intensifying stage of Edward. And you can see this is hybrid system, this is operation HWRF. You can see a big difference coming from the analysis and the subsequent forecast. So, and then we did basically found, compared to operation or HWRF, the hybrid analysis has a stronger inertial stability, red color, smaller radius maximum wind, stronger tangential wind, and shallower inflow layer. So all this are consistent with the earlier theoretical study, what an intensifying storm should look like. Okay, basically, the storm analyzed by the new hybrid approach is able to provide the analysis which is more realistically representing an intensifying storm compared to the operation HWRF. So it's not just an accident, it's better. There is a reason behind it. That's the point I want to share. Okay. So with this new hybrid system, then we are able to study the impact of a variety of observations. So Patricia 2015, it was a notoriously difficult hurricane to predict because of the small size and its rapid intensification. So this is the GOES 13 band 4 image, okay? And all the other panels are the 12-hour forecast, okay? 12-hour forecast. So these are all the simulated GOES 13 band 4 image, basically. These are all forecasts. So this is after assembling operational observations. So you're still seeing the storm is too big compared to the reality, and the eye is too big. So and I'm just giving you 2 examples. Here you're assembling the tail Doppler radar on board of P3 aircraft. And this is assimilating the job sounds released from outflow layer, okay, by the WB-57 aircraft. You can see this after assimilating observations, you're able to correct the structure of the storm, okay? So they now look better or closer to the observation. So, okay. So that's illustrating the usage of the DA, okay, you can actually use it to study the impact of the data for NWP problems, for example. But another powerful thing you can do for DA is you can use it to review model problems, okay? For example, this is Patricia, and this is our observation from the aircraft. This is our analysis after the hybrid data simulation. And this is background without doing any assimilation of the data. And this is using the operational vortex modification approach. You can tell from comparing D with this, this is more realistic, right? It's closer to observation. And this one is, producing an analyzed storm which is too big, too strong, okay? So then when we look at the forecast, we were completely shocked when we look at this, because the forecast initialized from the beta analysis was actually worse, okay? You see a large spin down. But if you look at the vortex modification initialized forecast, it's not having such a big problem here. So what's going on here? So we look at the second circulation, okay, every 2 minutes. And what we found basically, okay, if you initialize the forecast from vortex modification, yeah, at the first 4 minutes, the model struggled, but it was able to quickly spin up the second circulation at 1 hour. But if we use the analysis, okay, produced by hybrid DA, you're seeing, okay, one thing is that your outflow layer is elevated. Okay, this is consistent with our observation. And however, model just struggled to spin up a second circulation. So even for 1 hour, it's just not able to spin up second circulation. So model just struggled with spin down. Okay, so we looked at and we found, okay, very likely this is coming from model physics deficiency. So our analysis, okay, is able to produce this vertical oscillation of the subgradient and supergradient. This is a theoretical model. And this is vortex modification. You don't see a resemblance of that compared to that, okay? So after diagnostic, we found this is very likely because horizontal diffusion of H-warp is too strong, so it's not supporting this inflow-outflow oscillation in the vertical. Another thing we found is the problem with H-warp boundary layer, okay? So basically, when we look at the total condensate over the first hour, we found basically there's a discontinuity of the turbulent mixing at the boundary layer top, which tends to constrain the communication between boundary layer and the moisture and heat transport above the boundary layer top. So when we use this Ping-Zhu approach with turbulent layer mixing, it's now able to allow the moisture and heat transport between the fluid atmosphere and the boundary layer. So this is, okay, to prove that hypothesis, we basically replace the the old physics with the new physics. For example, we we reduced horizontal diffusion. We actually use the new boundary layer scheme. Okay, this both can actually improve or alleviate the spin down issue. So this thing basically improve hardware forecast. Okay, it's not just sufficient to have improved analysis or data simulation. You need to have accompany the advanced DA with the advanced model physics or model to improve the entire package of the rapid intensification forecast. Okay, this is just illustration of using DA to review the model problem and how to fix that. I'm going to skip this. Okay, now summary ongoing work. I shared the cost-effective valid time shifting approach, and it shows improvement compared to the current configuration. We have other topics ongoing, which I don't have time to talk about it. One is multi-resolution for the EnVar, the other is field-dependent localization. And for convection data simulation, I introduced the new approach to simulate reflectivity directly. I also shared that using final resolution for a simulation is critical, okay, for the timing and weakening of the intensification of the tornadic supercell case that I showed. We have ongoing efforts of doing a simulation by combining both the GOES-R all sky radiances, including both clear and cloudy, with the radar observations. And algorithm development, for example, improve the static covariance for convective scales, and improve added inflation for convective scales, and also multi-scale data simulation for regional convection-allowing prediction purpose. For hurricanes, I showed a new hybrid D system for H-Dwarf and talk about why it could potentially improve the intensity forecast. And we also use that to review the problem in the model, okay, which is another significance for data simulation. So we're trying to alleviate some of the nonlinearity and Gaussian issue for hurricanes, like how to do IU in a hurricane framework where linearity is going to play an important role, which is not negligible. We're also dealing with ground-based radar simulation for landfalling hurricanes. Okay. For future work, at least the areas we like to work on, including the multi-scale, multi-resolution assimilation for both global and regional convection-scale prediction, develop methods to treat the nonlinearity and Gaussianity, continue UCA to review correct model errors. And we're also very excited about combining satellite with radar observations for convective-scale prediction. And we're leaning toward using LES resolution models to do data simulation to see, how we can take advantage of data and also to see how it's going to improve very fine resolution prediction. And finally, machine learning and data simulation combination. How we take advantage of machine learning through data simulation or apply it in data simulation. And apply it for a variety of NWP problems like global hurricane or convective scales. That's all that I have. Sorry, taking a little bit longer than I thought, but I'm done. Thank you.
Very impressive. This is total outsider to this field, but it looks like you've taken on really a lot of work in this area. So my question is that it looks like you keep showing results that you get more data, you get assimilation, you seem to keep improving. I'm just wondering, is there a point at which you reach a point of minimal return in which you spend all this effort in computation? Does it always give you an improvement? It seems to me the case that you always get improvement, but there must be some cases in which certain data, because of the nature of the data, because of the incompatibility of the model, that actually we reduce your forecast by increasing more. So I'm just wondering, did you find cases like that in which selecting the right quantity to improve actually make your prediction better, rather than keep on throwing more and more? Yeah.
Very good question. Actually, for example, radar simulation, the data is having very fine resolution. We are doing thinning. Okay, we thin the data to we do thinning, for example, thin it to like 2 or 3 kilometers or even 6 kilometers before we assimilate. Because we found if we are not doing any thinning, after we do the assimilation, it's degrading the forecast. So and for this hurricane example, we're simulating the drop zones from the WB-57 aircraft. It has very, very fine resolution in the vertical. So if we're not doing any superorbiting or thinning, okay, we just take the data into the model, you're going to see very bad results. The model cannot take that. Yeah. And it could be because the model is not fine. The resolution of the model is not matching the observation. That's one thing. I think there's still, limitation for the current data simulation approach to effectively using so much data.
Or the physics of the model.
Yeah, and also the physics. Exactly. The physics cannot. I just show you an example. Exactly. So the model physics is not, it's not accepting the information from the observation properly. I mean, the data simulation can take the observation in, so the storm can look very complex, consistent with observation. But the model physics is not advanced yet to be compatible with the complex structure produced by data simulation. So yeah, I do see that. Yeah, I do see degradations if you're not doing a good job for treating the observations, or you're not doing a good job to take care of model physics, or you're not doing a good job to finding the right parameter used for data simulation itself. So it's not always improving. That's for sure.
Hard work that you haven't shown that it's not improving, I guess.
Yeah, I think most of I guess my point is here is not so much how much data I should use. Mostly it's sharing the algorithm, data simulation algorithm itself. But for data simulation, how to treat data is a big chunk of work that needs to be sorted out.
Yeah, so it's really a wonderful work. One thing you mentioned that data assimilation help the climate prediction. Do you have any experience? Yeah, and experience how we do that? We tried, struggled, and very much still. We Kyle and we discussed several years, right? We still struggle how to really.
You are the expert to answer that question.
No, no, I need you guys' help with that.
Yeah, I personally have not done work on using DA for climate predictions yet. So my area is mostly on NWP weather, like from sub-hour to week 2. But for DA, I mean, there are many problems for climate predictions with DA. But one thing I can think of, which is a challenge, is how to do the coupled system simulation, especially you're dealing with systems which are having 2 different scales. How would you use information from one system which has very different scale to update the other one? I think the current ensemble-based approach would struggle that, because if you're having sampling error, for example, it may not take care of these coupled simulation, the cross-system covariance very well. So there is a big challenge there. That's the first bullet I listed as challenge for data simulation. Yeah, I think there are some studies to deal with that. I think that's just one of the problems. Yeah, there are more problems. So I think when the field is more advanced towards doing multi-scale, including coupled simulation algorithm development, that should help on the climate prediction for that particular aspect. But I know the climate model has its own issue, I guess. You could use DA to, determine the parameter better. So that could be another way in terms of using DA to improve climate modeling prediction. I don't have a good answer, but I can list a lot of challenges, as you would think. Yeah. Okay.
So you kind of focus on wide scale in spatial.
Yeah, that's true.
Could you comment on
yeah.
Because the climate has
yeah, it's actually it's okay. I only showed the spatial multi-scale, but even for storm scale, you're dealing with temporal multi-scale as well. For example, you yeah, yes, in a sense. But what I'm thinking in the mind is like your radar is seeing storms, right? It's doing every 5 minutes sampling, but the radar also sees large scale errors as well, right? How would you use this fine scale information in time? Okay, to correct the large scale, large scale in both space and time. So there's this aspect of time, multi-scale in time as well. I think, people have to start looking at the multi-scale in space more than the time, but that will be the next thing to look at actually. That's why I listed as part of future work there. Yeah, I think we can borrow some ideas from the spatial multi-scale to the time space. Yeah, I agree.
Any other questions? Otherwise, let's start the speaker.
Thank you.
Spatial grammatical over NOAA. So if you would like to interact, please contact us directly.
Nice to meet you.